We're on the final video series of sketching a curve without a calculator using all of our key features of derivatives. So we have a new function. It is a rational function. And to begin, we need to find f prime and f double prime of x per the usual. F prime of x would be 10 thirds x to the 2 thirds minus 20 thirds x to the 1 third. And we do have a GCF of 10 thirds x to the 1 third, which will help us with solving later on. So that leaves us x to the 1 third minus 2. So we will be referencing that piece when we go to solve. Now to find f double prime, we will be using the first line of our derivative here. So then that'd be 20 ninths x to the negative 1 third minus 20 ninths x to the negative 2 thirds. So then at that point, we want to go ahead and get a denominator going of 20 over 9x to the 1 third minus 20 over 9x to the 2 thirds. And we're needing an x to the 1 third to get a common denominator. So if we get an x to the 1 third, we need to multiply the denominator by x to the 1 third, which gives us x to the 2 thirds. So then in the end, we have a GCF of 20, and that leaves us with x to the 1 third minus 1 divided by 9x to the 2 thirds. So now we have our key information for when we need that from our derivatives. So let's start out with our initial information, x-intercepts. So x-intercepts would come from our initial function equaling 0. So 0 equaling 2x to the 5 thirds minus 5x to the 4 thirds. We do have a GCF of an x to the 4 thirds. And if we factor that out, that leaves us 2x to the 1 third minus 5. So if x to the 4 thirds equals 0, x is equal to 0. If 2x to the 1 third minus 5 equals 0, then 2x to the 1 third is equal to 5 divided by 2. And then to solve for x, we should cube that. So that's 125 over 8, or approximately, we'll go with an exact 15 and 5/8. So then our y-intercept would be 0, 0. Symmetry. We don't have symmetry. We don't have a vertical asymptote, and we don't have a horizontal asymptote, and that's because we're dealing with a rational function, or radical function, sorry, and not a rational function. So now we need to pull out our possible points of inflection and critical numbers. Critical numbers will come from prime, and prime is equal to 0 at 0 and 8. So that all comes from the first derivative. And then our possible points of inflection would come from our second derivative, and our second derivative is undefined at 0. And our other point of inflection would be 1 from the numerator. So now we have all of our key information. So we're going to go build our table now. So we have our table. And again, we'll have the values we want to test. We'll have our f of x if it applies, f prime of x, f double prime of x, and then our conclusion. And then our intervals will be negative infinity to 0. At 0, we do need to test that. Then we'll go from 0 to 1, and 1 is a possible point of inflection, so we do need to test x equals 1. 1 to 8, we need to test x equals 8, and then we're going to run from 8 to infinity. So now that we have our intervals, we'll fill out the remaining portions. And keep in mind, we will not test a function on an interval. Hopefully this is all starting to make perfect sense. Let me know if you need some assistance. I am happy to help. But again, we're crossing out our intervals because you can only test the function at a value, not over an interval. So now at 0, we know our function is 0. Sorry about that. At 1, if we were to plug in 1, we get -3 for our function. At 8, we get -16 for our function. So that's plugging the x value into the initial function to figure out the y values. So now, on the interval -infinity to 0, let's say -1. Prime is positive, double prime is negative. Because prime is positive, we know our function's increasing. And because we know double prime is negative, we know this is con down. At 0, f of x is 0. F prime of x is 0. F double prime is undefined. So it fails the second derivative test. Therefore, we're going to have to now look at comparing our intervals here in a minute. So from 0 to 1, let's say a half. F prime would be negative. F double prime is negative. So it was a possible point of inflection or a critical number. So if we hone in on prime here, and I'm going to highlight our two pieces, we're going from positive to negative. So because we're switching from positive to negative, that means that we have a relative maximum because we're switching from increasing to decreasing. Now our concavity did not change. That's why it's not a point of inflection, because we're both con down on the intervals. So here we are decreasing. Sorry, I forgot the color I was using. We are decreasing and con down. So then at 1, we're at -3 for our function value, and we're at a negative for prime and 0 for double prime. So again, we failed the second derivative piece, but that makes sense because this was a possible point of inflection. So now let's look at double prime as we change along. On the interval 1 to 8, so let's say 2. Prime of 2 is negative, double prime of 2 is positive, so we are decreasing and con up. Now let's go back and refer to prime over our interval. So we're switching from con down to con up, so that makes our point a point of inflection. And that's due to the change in our concavity. So now, at 8, we have -16 for our function value, 0 for our f prime value, and a positive for our double prime value. So we know it's a critical number because prime was equal to 0. And now we know that we're concave up, which indicates we have a relative min according to the second derivative test. And then on our interval from 8 to infinity, so let's say 9, prime at 9 is positive, double prime at 9 is positive, therefore we're increasing and we're concave up. So last but not least, let's go ahead and sketch a rough sketch of our function. So we need our x and our y-axis. And all of our values were positive. So I'm going to go ahead and switch to a majority positive x-axis. Just a little bit of our x-axis being negative behind us. I also know that I have extreme negative values for our y's. So I'm actually going to distort my axis like this. At 0, we know our function is equal to 0. On the interval from negative infinity to 0, we know that we're increasing and con down. And then at 1, -3, we know that we have a point of inflection, meaning we're going to switch from concave down to concave up. So we are concave down, and then we're going to switch to concave up. But we do need to get to our other value. So I'm going to do something we do in mathematics every now and again and put a break. Then I'm going to put 8. That's just to help me out. I'm going to do another break. And then I'm going to put -16 down here. So basically, I'm not counting everything out. I'm just getting our rough point here. So then we have a concave up and decreasing portion after our point of inflection at 1, -3. And then at 8, -16, we switch to concave up and increasing. And we do go through our other intercept of -15 and 5/8, 0. Or sorry, 15 and 5/8, not negative. So this is a rough sketch of our function then over our interval. Make sure you ask questions if you have them. I'm happy to answer them. For your homework, I would like you to just attempt this last example, which is a polynomial, so it should be one of the easier functions to sketch. Go ahead and sketch this to me. I will be asking you to send me your solution. So please sketch this polynomial. This is your homework. So your homework is one whopping problem. Please get back to me if you have any questions about it. Happy to help. Appreciate you taking time out of your day to watch this series. Thank you.